Imagine that a single particle of light has just completed the longest journey any light can make to reach us. It arrives without weight, without memory, and without a clock. Yet hidden in its color is a record of almost the entire history of the cosmos. Cosmologists examine that record and issue the first receipt for its journey. The universe is about 13.8 billion years old. The photon has been traveling for almost all of that time, beginning its free flight when the young universe first became transparent. Nothing carrying information can pass through its local surroundings faster than light. So ordinary arithmetic seems to set an unavoidable limit. If light has had less than 13.8 billion years to travel, the most distant visible region should be less than 13.8 billion light-years away. Look in the opposite direction, double the radius, and the observable universe should be no more than 27.6 billion light-years across. But cosmologists issue a second receipt. According to the standard model built from measurements of cosmic expansion, the present radius of the observable universe is not 13.8 billion light-years. It is approximately 46.5 billion light-years. From one side of our observable region to the other, the present distance is therefore close to 93 billion light-years. The numbers seem impossible together. A universe only 13.8 billion years old appears to have become wide enough that even light would need 93 billion years to cross it. The obvious escape is to imagine that something broke the speed limit. Perhaps the oldest galaxies raced away from us faster than light. Perhaps the Big Bang exploded from a central point with such violence that matter crossed space at impossible speed. Or perhaps the 93 billion light-year figure is only a dramatic estimate, repeated until it began to sound like a measurement. None of those explanations gives the real answer. The age is not a casual guess. It comes from a cosmological model tested against the ancient microwave light covering the sky, and against other observations of expansion. The 93 billion light-year diameter is not invented either. It is a rounded value, derived from that same expansion history. But it does not describe a wall that astronomers have photographed, and it does not tell us the size of the entire universe. It describes the present diameter of the region from which signals could have reached us, interpreted through our best large-scale model of spacetime. The paradox survives because two reliable numbers are being placed into an unreliable rule. On Earth, the rule works perfectly. If a beam travels for 1 second through a laboratory, multiply its speed by 1 second and you obtain the distance covered. The laboratory does not grow significantly while the beam crosses it. The ruler used at departure still means the same thing at arrival. Time, speed, and distance fit together exactly as intuition expects. Across the universe, one hidden assumption fails. The arena is not static. That statement is often compressed into 3 words. Space itself expands, but those words can conceal more than they explain. What expands? Relative to what? If the distance changes while the photon is traveling, which distance belongs on its receipt? There is the time the photon spent in flight. There is the sequence of local distances it crossed, always moving at light speed. And there is the separation, measured according to the cosmological model today, between us and the region that released it long ago. These are 3 different questions. Cosmology can give each of them a different answer without contradicting itself. Our arriving photon therefore carries 3 receipts. The first records nearly 13.8 billion years of travel. The second records locally ordinary motion, never faster than light. The third places its ancient point of origin tens of billions of light-years away, on the universe's present map. The mystery is not which receipt is false. The mystery is why we expected them to display the same number. To resolve it, we will have to abandon the picture of light crossing a motionless container. We will need to ask how distance is defined when the geometry between two locations changes, how astronomers reconstructed that change from relic radiation and exploding stars, and why relativity permits distant separation to grow in ways that no nearby object could imitate. The answer will not weaken the speed of light. It will reveal that our familiar definition of distance was never universal to begin with. Only then can 13.8 billion years and 93 billion light-years become parts of the same story. The first step is to separate two questions that ordinary language blends together. How long has the universe existed? And how far away is the most distant region that can have influenced us? In a static world, the answers appear almost interchangeable. In cosmology, they are not. The figure of 13.8 billion years is an age. More precisely, it is the elapsed cosmic time between the early hot, dense state described by the standard cosmological model and the present. It is not obtained by finding the oldest visible object and reading a date from it. Cosmologists infer it by fitting a model of expansion to several kinds of evidence, especially the cosmic microwave background. Under the standard model and the parameters measured by the Planck mission, the age is approximately 13.8 billion years. A light year, despite its name, measures distance. It is the distance light crosses through its local surroundings in 1 year, roughly 9.46 trillion kilometers. Saying that the universe is 13.8 billion years old, and saying that something is 13.8 billion light-years away, therefore describe different physical quantities. They become connected only after we specify what distance means and how the geometry behaves while light is traveling. Suppose we observe a distant galaxy whose light has been traveling for 10 billion years. That 10 billion year interval is its lookback time. We are seeing the galaxy as it was when the light began its journey, not as it is at this moment. Multiplying the lookback time by the speed of light gives a useful light travel distance, but it does not automatically give the galaxy's separation from us when the light was emitted, and it does not give the separation we assign to its location today. Those are different questions, because the distance between widely separated regions changes during the journey. Imagine placing ideal markers throughout the cosmos, each carried along with the average expansion. A marker may remain at the same address on a cosmological coordinate grid, even while the measured spacing between neighboring addresses grows. Cosmologists call this fixed grid separation a co-moving distance. It factors out the overall expansion and lets the same large-scale location keep one coordinate through cosmic history. Proper distance asks a different question. How much separation would the cosmological model assign between two locations on a particular slice of cosmic time? At earlier times, when the universe's scale factor was smaller, the proper distance between two co-moving markers was smaller. Today, cosmologists conventionally set the scale factor equal to 1. With that normalization, present proper distance and co-moving distance have the same numerical value. This is why the familiar radius of approximately 46.5 billion light-years is often called the present co-moving radius of the observable universe. It does not mean that we can see a region 46.5 billion light-years away as it exists today. The light arriving from near that limit carries information from the distant past. The number describes where the corresponding co-moving location lies on today's reconstructed cosmic map. Observation provides the ancient signal. The cosmological model connects that signal to a present distance. This also explains why the word observable requires care. The observable universe is the region from which some causal influence could have reached a particular observer during cosmic history. It is centered on us because we are the observer making the map, not because Earth occupies a special center of all space. An observer in a distant galaxy would possess a different observable sphere centered on that galaxy. The two spheres could overlap, but their boundaries would not be identical. The boundary is known as the particle horizon. It marks the greatest present co-moving distance from which a signal could, in principle, have reached us since the earliest stage included in the model. The oldest electromagnetic signal we actually observe is the cosmic microwave background. It was released when the universe became transparent, about 380,000 years after the hot Big Bang. Its source surface lies slightly inside the theoretical particle horizon, because ordinary light could not travel freely through the earlier opaque plasma. Neither surface is a physical wall. Crossing our particle horizon would not require breaking through a shell. There may be galaxies, matter, and continuing space beyond it. Their signals simply have not had the required causal history to reach us. The observable universe is therefore a limit on information, not necessarily a limit on existence. That distinction corrects another hidden assumption in the title. 93 billion light-years is not a measured diameter of the entire universe. It is approximately twice our present particle horizon radius under the standard cosmological model. The total universe could be vastly larger. Depending on its global geometry and topology, it might even be spatially infinite. Current observations cannot turn the observable diameter into a total size. We can now label the photon's three receipts more carefully. The first reports lookback time, nearly the age of the cosmos, for the oldest freely traveling light. The second concerns the photon's local journey. Every nearby observer along its path measures it moving at the speed of light. The third reports present co-moving separation, where the emitting region belongs on a map constructed for the current cosmic time. No receipt replaces the others. They answer different questions, and each question requires its own definition. The preliminary resolution is therefore simple. The universe did not need to fit 93 billion years of light travel into 13.8 billion years of time. The 93 billion light-year figure is a present diameter across a region whose distances evolved while the signals were moving. The photon traveled locally at the permitted speed, even as the relationship between its origin and our present ruler changed. But this answer still leaves the most important part unexplained. Saying that distance evolved does not show how it evolved, why expansion changes the conversion between travel time and present separation, or why the final radius is about 46.5 billion light-years rather than 20 billion, 60 billion, or some other value. To understand that, we need a way to describe locations that remain identifiable, while the scale between them changes. We need to follow light across that changing scale, without pretending space is a material substance. And we need to discover which part of our familiar distance equation survives when the universe itself refuses to remain geometrically still. To describe a universe whose distances change, cosmologists begin with an imaginary network of markers. These markers are not stars, because stars have their own local motions. They are not particles embedded in a cosmic material. They are reference points chosen to follow the average large-scale expansion, as though each one were carried peacefully with the overall flow of the universe. Give every marker an address. On this coordinate map, the addresses remain fixed. A marker labeled 1 stays at 1. Another labeled 2 stays at 2. Yet the physical separation assigned between those addresses can increase with time. The fixed difference between their addresses is called their comoving separation. The changing physical separation on a selected cosmic time slice is called their proper distance. One quantity connects them: the scale factor. Cosmologists usually write the relationship as proper distance equals the scale factor multiplied by comoving distance. The scale factor is represented by the letter A, and it describes how the characteristic spacing of the large-scale universe changes over time. By convention, its value today is set to 1. If it was 1/2 at some earlier epoch, two markers with a present separation of 1 million light-years had a proper separation of roughly 500,000 light-years at that time, assuming they followed the expansion perfectly. Cosmic expansion does not make every object grow. Electromagnetic forces hold atoms together, while gravity binds planetary systems and galaxies. The scale factor describes sufficiently large separations after motions are averaged away. It is not a prediction that people, planets, or rulers expand. The coordinate grid is therefore a bookkeeping device, not a substance. It can be pictured as lines whose spacing changes, but nothing requires literal lines to exist in space. The universe is not a rubber sheet being pulled from outside. The model does not say what the universe is expanding into. It describes how measured separations between co-moving locations evolve within spacetime itself. Now place a photon on this changing grid. At every point along its journey, a nearby observer measures the photon moving at the speed of light. This is not an approximation and not a rule that expansion suspends. Locally, relativity works exactly as expected. If the observer constructs a small laboratory, measures a short distance, and times the photon crossing it, the result is always c. But the photon is not crossing one small laboratory. It is passing through a chain of local regions, while the large-scale relationship among those regions changes. Its progress toward us must therefore be described by two effects at once. The photon moves through the comoving grid, and the proper spacing represented by that grid evolves. Consider a simplified example. Imagine the photon is heading toward us, while the proper distance between its current location and ours is increasing. This can happen when the expansion adds separation across the enormous interval faster than the photon removes it by locally advancing toward us. The photon is still pointed in our direction. It is still moving locally at c, yet its proper distance from us can temporarily grow. Later, if the expansion rate changes, the photon's local progress may begin to win. Its proper distance can reach a maximum, and then decrease until the photon arrives. This is one reason a simple diagram of an object moving through fixed space fails. The photon's local direction, its coordinate progress, and its proper distance from us do not have to behave in the same way at every moment. Redshift gives observers a crucial trace of the scale factor's change. When light travels across the expanding universe, its wavelength is stretched. In the ideal large-scale model, the ratio between the wavelength we observe and the wavelength at emission is related to the ratio of the scale factor now to the scale factor then. A source observed at redshift 1 emitted that light when the scale factor was roughly half its present value. A source at much greater redshift reveals an epoch when the characteristic cosmic scale was much smaller. Not every redshift is cosmological. Local motion and gravity shift light. Across scales, however, the redshift pattern records cosmic evolution. The rate of that evolution is summarized by the Hubble parameter. It tells us the fractional rate at which the scale factor is changing at a particular cosmic time. The Hubble parameter is not one permanent speed for the entire universe. Its value changes over history. Nor does it say that every object recedes from us at the same speed. At a given time, the recession rate assigned by the large-scale model increases with proper distance, while local motions remain superimposed upon that flow. This changing rate matters, because the photon crossing the universe experiences not one expansion condition, but an entire sequence. It travels through an early universe dominated by radiation, a later era dominated by matter, and a recent era in which dark energy strongly affects the expansion. To convert its travel time into a present co-moving distance, cosmologists must account for the scale factor throughout that journey. A useful way to anticipate the calculation is to divide the path into tiny intervals. During each tiny interval of cosmic time, the photon crosses a small local proper distance at c. But if we want to express that step using today's co-moving ruler, we must consider the scale factor when the step occurred. An early step took place when all co-moving intervals represented much smaller proper separations than they do now. The same local step therefore corresponds to a different amount on today's coordinate map than a step taken recently. Adding those converted steps produces the total co-moving distance the photon could have covered. Cosmologists express that sum with an integral, but the underlying idea is simple. Preserve light's local speed, record how the scale changed at every stage, and translate the entire path into one consistently defined present-day distance. This also reveals why the phrase "space expands" can mislead. It sounds as though expansion is an extra wind pushing galaxies and photons. In the cosmological model, expansion is not an additional velocity that a photon feels blowing against it. It is the evolving relationship between co-moving coordinates and proper distances. The photon follows the geometry, moving locally at c throughout. The model assumes that, across sufficiently enormous regions, the universe is broadly homogeneous and isotropic. Galaxies, clusters, and voids dominate locally, but large-scale observations support one common scale factor as an extraordinarily successful approximation. We now possess the minimum vocabulary required by the paradox. A co-moving address can remain fixed. Its proper separation can change. The scale factor connects those descriptions. Light remains locally limited to c while crossing the evolving geometry. Redshift helps reveal how much the scale has changed, and the Hubble parameter describes how rapidly it changes at each epoch. Yet a vocabulary is not evidence. A flexible mathematical grid could describe many imagined universes. Why did scientists abandon the older picture of fixed space? Why trust a dynamic geometry at all? The answer did not begin with the 93 billion light-year puzzle. It began when a theory of gravity and a set of difficult astronomical measurements independently made a static cosmic stage impossible to maintain. For most of human history, treating space as an unchanging stage was not a mistake. It was an extraordinarily successful approximation. In everyday life, a meter remains a meter while an object crosses it. Clocks can be synchronized without worrying about the curvature of spacetime. The same geometry describes a room today and tomorrow. Newtonian physics turned this intuition into a powerful rulebook. Space provided a fixed arena. Time advanced uniformly, and matter moved under forces. With those assumptions, scientists could predict falling bodies, planetary orbits, tides, and the paths of comets with astonishing accuracy. Nothing in ordinary experience suggested that the arena itself should evolve. Even astronomy offered little reason to think otherwise. Stars shifted across the sky, planets wandered, and comets returned, but the larger stellar background appeared permanent. Into the early 20th century, many scientists pictured the universe as eternal and broadly static. The Milky Way was often treated as either the whole universe or its dominant structure, while the true nature and distance of the faint spiral nebulae remained disputed. Then gravity acquired a different meaning. In 1915, Albert Einstein completed general relativity. Gravity was no longer simply a force acting across a fixed stage. Matter and energy influenced the geometry of spacetime, and that geometry guided motion. When Einstein applied the theory to the universe as a whole, static solutions proved difficult. A cosmos filled with gravitating matter would not naturally remain balanced forever. Einstein introduced a cosmological term into his equations to permit a static model. Later retellings often claim that he called this his greatest blunder, but the exact quotation is historically uncertain. What matters scientifically is that the static solution required careful balancing and was unstable. A slight disturbance would drive it away from equilibrium. Other physicists were willing to let the universe move. Beginning in 1922, Alexander Friedmann published solutions to Einstein's equations, in which the cosmic scale changed with time. Depending on the contents and geometry, the universe could expand, contract, or follow different histories. These were mathematical possibilities before decisive observations existed. They demonstrated that general relativity did not demand an eternal, motionless cosmos. Georges Lemaître went further. In 1927, he independently developed an expanding solution and connected it with astronomical data. He argued that the redshifts of distant nebulae could reflect a universe whose large-scale distances were increasing. He even estimated a relationship between distance and recession, 2 years before Edwin Hubble's famous publication. But none of this could become convincing without a way to measure distances beyond the Milky Way. That crucial ladder began with Henrietta Swan Leavitt. While studying variable stars in the Magellanic Clouds, Leavitt discovered that Cepheid variables with longer pulsation periods possess greater intrinsic luminosities. If astronomers could calibrate that relationship, a Cepheid's period would reveal its true brightness. Comparing true brightness with apparent brightness would then indicate distance. Leavitt's result transformed pulsing stars into cosmic mileposts. It did not by itself establish expansion, but it made the later distance scale possible. At the same time, Vesto Slipher was measuring spectra from spiral nebulae. He found that many displayed substantial redshifts, meaning their spectral features were displaced toward longer wavelengths. In a motion-based interpretation, most were receding at remarkable speeds. Slipher supplied much of the early velocity evidence later used in studies of cosmic expansion. although simplified histories frequently reduce the discovery to a single name. The scale of the universe changed decisively when Hubble identified Cepheid variables in the Andromeda Nebula. Their brightness showed that Andromeda lay far beyond the Milky Way. The spiral nebulae were not nearby clouds inside our galaxy. They were galaxies in their own right, separated by immense distances. Astronomers could now compare distance estimates with redshift measurements. In 1929, Hubble published evidence for a roughly linear relationship. The more distant a galaxy appeared, the greater its recession inferred from redshift. His sample was small, the distances were uncertain, and the numerical expansion rate was far above the modern value. Yet the pattern provided an observational foundation for an expanding universe. Early measurements also contained serious uncertainties. Cepheids required calibration, intervening dust altered apparent brightness, and nearby galaxies carried local motions that could obscure the broader expansion pattern. The first numerical estimates were therefore not precision cosmology. Their importance lay in the relationship they exposed. As telescopes improved and distance indicators were recalibrated, the value of the present expansion rate changed dramatically, but the large-scale correlation survived. Scientific progress did not preserve every early number. It preserved the dynamic picture that continued to explain better measurements, while the static alternative lost its observational support. This history is better understood as convergence than as one sudden discovery. General relativity made dynamic geometry possible. Friedman developed expanding mathematical models. Lemaître joined theory to redshift and distance data. Leavitt supplied a way to estimate extragalactic distances. Slipher measured the redshifts. Hubble and collaborators extended the distance evidence and demonstrated the relation more visibly. Each contribution solved a different part of the same problem. The modern name Hubble-Lemaître Law reflects part of that shared history. On sufficiently large scales, recession rate is proportional to proper distance at a given cosmic time. The proportionality factor is the Hubble parameter, whose present value is called the Hubble constant. This relation does not place Earth at the center. In an approximately homogeneous expansion, an observer in another galaxy also sees distant galaxies receding, with greater distances corresponding to greater recession rates. A simple analogy can show why, without turning the universe into a material balloon. Imagine a line of evenly spaced addresses whose separations all double. Every address sees every other one move farther away. The farther apart two addresses began, the more additional separation appears between them. No address must be the central origin of the change. The analogy captures the relationship among separations. Although real cosmology uses three-dimensional curved spacetime rather than a stretching line. Redshift also required more careful interpretation than an ordinary Doppler shift. A nearby source moving through space can stretch its light waves through relative motion. Across cosmological distances, redshift is described within an evolving geometry. The scale factor changes while the light propagates. Peculiar velocities still matter, especially nearby, but the large-scale pattern carries information about cosmic expansion. The old static rulebook had not become useless. Newtonian physics remained accurate for countless local problems. Even special relativity continued to govern local measurements of light and motion. What failed was the assumption that rules tested within a nearly unchanging local environment could be applied unchanged across the entire history and scale of the universe. Expansion, however, created a new problem. The early redshift distance relation described the universe near the present epoch. It did not tell scientists how rapidly the scale factor changed billions of years ago. If the rate had remained constant, one age and one horizon would follow. If gravity slowed the expansion, another would follow. If some unknown component later accelerated it, the result would change again. To calculate how far ancient light could reach, cosmologists needed the whole curve, not merely its slope today. The sky eventually provided records from radically different eras. One arrived as a nearly uniform microwave glow, released when the universe was young. Another came from dying stars, visible across billions of light-years. Together, these observations would reveal that expansion had not simply continued. Its behavior had changed, and the changing rate would become essential to understanding why the oldest light now belongs on a map far larger than static intuition allows. An expanding universe raised a question that the first galaxy surveys could not answer. Was the expansion always happening at the same rate, or had its behavior changed over time? The difference was fundamental. Matter attracts matter through gravity. In a universe dominated by matter, that attraction should slow the expansion, even if it never fully reverses it. The present rate could therefore not be projected backward as a straight line. To recover the path of an ancient photon, cosmologists needed evidence from earlier cosmic eras. The first great record did not arrive as visible starlight. It filled the entire sky in microwaves. During the 1940s, researchers developing the hot Big Bang picture recognized that an early dense universe should have been filled with intense thermal radiation. As expansion continued, that radiation would cool, and its wavelengths would stretch. Ralph Alpher and Robert Herman made an early estimate of the remnant temperature, building on work associated with George Gamow's research program. The prediction was not immediately transformed into a major observational campaign, and its significance faded from broad attention. In 1965, Arno Penzias and Robert Wilson were working with a sensitive radio antenna at Bell Laboratories. They encountered a persistent background signal that appeared in every direction. They investigated equipment, surroundings, and possible interference, but the excess remained. Nearby at Princeton, a group led by Robert Dick was preparing to search for relic radiation from the early universe. The connection between the unexplained signal and the cosmological prediction was soon recognized. The cosmic microwave background became decisive evidence that the universe had once been much hotter and denser. This radiation does not come from the first instant. For roughly the first 380,000 years of the hot Big Bang history, the universe contained a hot plasma of free electrons and atomic nuclei, photons scattered repeatedly from charged particles. The cosmos was not transparent in the way it is today. As expansion lowered the temperature, electrons combined with nuclei to form neutral atoms. Photons could then travel far more freely. That transition, called recombination, released the light we now observe as the microwave background. Expansion has stretched its wavelengths by more than 1,000-fold. Radiation that began largely in visible and infrared wavelengths now arrives as microwaves with a nearly perfect thermal spectrum at about 2.7 Kelvin. Tiny temperature variations across the sky preserve information about density differences in the young universe. Those variations later helped seed the structures that became galaxies and clusters. The microwave background gave cosmologists both a picture and a measuring system. COBE established the precision blackbody spectrum and detected large-scale anisotropies. WMAP mapped those temperature differences in far greater detail. Planck later measured temperature and polarization patterns with still greater precision. The angular structure of the fluctuations encoded the contents, geometry, and expansion history of the universe. Yet the microwave background alone did not make cosmic history simple. A model could fit the early universe and still require tests at later times. According to the expected matter-dominated picture, expansion should gradually decelerate. Astronomers needed objects bright enough to be seen across billions of light-years and regular enough to compare across distance. Type 1 supernovae offered that possibility. These explosions occur in systems involving white dwarfs, although the exact progenitor pathways are not all identical. Their peak brightnesses are not perfectly uniform. However, relationships between the shapes and colors of their light curves allow astronomers to standardize them. After corrections, their apparent brightness can be used to estimate relative distance. Their spectra also reveal the redshift of the host galaxy, indicating how much cosmic expansion occurred while their light traveled. During the 1990s, two major collaborations pursued distant Type 1a supernovae, the Supernova Cosmology project and the High-Z Supernova Search Team. The work demanded coordinated observations. A faint transient had to be discovered, classified, followed as it brightened and faded, and separated from the light of its host galaxy. Dust, detector calibration, supernova evolution, and selection effects all had to be considered. The expectation was straightforward. If gravity had been slowing expansion, sufficiently distant supernovae should show a brightness redshift relationship consistent with stronger deceleration in the past. Instead, the distant events appeared dimmer than the decelerating models predicted. Both teams reported evidence in 1998 that the expansion was accelerating. The conclusion did not mean individual galaxies had acquired engines pushing them outward. It meant the scale factor's evolution could not be reproduced by a cosmos containing only ordinary matter and dark matter with negligible pressure. Within general relativity, the simplest addition was a cosmological constant, represented by the Greek letter lambda. Its energy density remains constant as space expands, allowing its relative influence to grow while matter becomes diluted. The unknown cause of the acceleration became known as dark energy. That name describes an inferred component or effect. It does not explain its microscopic nature even today. For the horizon puzzle, the key lesson is not merely that acceleration exists. It is that the expansion history contains distinct regimes. In the very early hot universe, radiation strongly influenced the rate. As expansion continued, radiation lost energy density faster than matter, and matter became dominant. During matter domination, gravity decelerated the expansion. Much later, a dark energy-like component became dynamically important, and the expansion began accelerating. These transitions were gradual, not switches thrown at exact universal moments. Each regime changes the relationship between cosmic time and scale factor. That relationship determines how much co-moving distance a photon accumulates during every stage of its journey. Two universes with the same present age could have different observable radii if their expansion histories differed. Two universes with the same current Hubble parameter could also have different ages and horizons if they reached the present rate along different paths. The oldest visible photon, therefore, passed through a sequence of changing conditions. It began free streaming near the end of the opaque plasma era. It crossed a universe in which matter increasingly shaped expansion and structure. It continued while stars and galaxies formed, while matter diluted, and while accelerated expansion emerged. Its present co-moving distance records the cumulative effect of that entire history. This is why the 46.5 billion light-year radius cannot be obtained from one telescope image or one measurement of today's expansion rate. It is inferred by finding a cosmological history consistent with many observations and then calculating how far signals could travel through that history when expressed on today's ruler. The CMB and supernovae perform different roles in that reconstruction. The microwave background anchors conditions near the beginning of the photon's transparent journey. Supernovae sample the comparatively recent universe and reveal late acceleration. Other evidence, especially baryon acoustic oscillations and the growth of structure, helps connect the eras. None alone supplies the complete answer. Together, they constrain the curve the scale factor followed. They also create a more subtle mystery. The microwave sky is remarkably uniform across regions that, in a simple, non-inflationary hot Big Bang model, appear not to have had enough time to exchange signals before recombination. This is the classic horizon problem. Its leading solution proposes an extremely early period of accelerated expansion called inflation. But that problem must not be confused with our title question. Inflation concerns the causal preparation of the early universe. The roughly 46.5 billion light-year particle horizon today is calculated mainly from the subsequent expansion history. By the end of the 20th century, the static cosmic stage had therefore failed twice. First, galaxy redshifts showed that large-scale distances evolve. Then, relic radiation and exploding stars showed that the evolution itself changes rate. The universe was not simply getting larger. Its contents continually altered how it grew. We can now identify what ordinary arithmetic omitted. Multiplying light speed by cosmic age treats every year of the journey as though it occurred on the same unchanging scale. It assigns equal present-day meaning to a year traveled when the universe was tiny, and a year traveled when the universe was near its current size. The observations tell us that those intervals cannot be converted so simply. The next step is to perform that conversion. We must break the photon's journey into small pieces, preserve the local speed of light in every piece, and translate each one through the scale factor that existed when it occurred. When the pieces are finally added, the apparently impossible radius will emerge not from a broken speed limit, but from the hidden arithmetic of changing geometry. The missing arithmetic begins with the smallest possible part of the journey. Take one brief interval of cosmic time and call it dt. During that interval, a photon crosses a local proper distance equal to c multiplied by dt. Nothing unusual has happened. A nearby observer measures the ordinary speed of light, exactly as relativity requires. Now ask a different question. How much of the fixed co-moving grid did that local step cross? Proper distance and co-moving distance are connected by the scale factor. If a particular interval on the co-moving grid has proper length today, the same interval had a smaller proper length when the scale factor was smaller. To translate the photon's local step into co-moving coordinates, cosmologists divide by the scale factor at the time of the step. The relationship can be written compactly. The small co-moving distance, dk, equals c times dt divided by a of t. Every symbol carries a clear instruction. The t preserves the photon's local speed. The dt records a small amount of cosmic time. The scale factor a of t tells us how today's co-moving ruler related to proper distance during that interval. Dividing by a converts the local step into the coordinate distance that will have the same numerical value as proper distance when the scale factor reaches 1 today. Early in cosmic history, a once was much smaller than 1. Dividing by a small number produces a larger co-moving interval. This does not mean the photon moved locally faster. It means that a fixed segment of today's co-moving map represented less proper distance then. The photon could cross more of those compact early grid segments during one local step. Imagine 2 periods, each lasting 1 million years. Suppose the scale factor during the first is 1/10 of today's value, while during the second it is 1/2. Locally, light crosses the same proper distance in both million-year intervals. On today's co-moving ruler, however, the first contribution is divided by 1/10, and the second by 1/2. The earlier interval contributes 5 times as much co-moving distance. The example freezes the scale factor inside each interval for clarity. In reality, it changes continuously. Cosmologists therefore divide the entire history into intervals so small that the scale changes negligibly within each one. They convert every local step, and then add them all. That continuous sum is an integral. The co-moving particle horizon radius is written as c multiplied by the integral, from the early boundary of the cosmological model to the present age, of dt divided by a of t. In symbols, key p equals c times the integral from 0 to t0 of dt over a of t. The upper limit t0 is the present cosmic age. The function a of t is the expansion history. The result, key p, is the greatest co-moving distance a signal could have crossed during the modeled history. Because the scale factor is normalized to 1 today, that co-moving result also gives the proper distance assigned to the horizon on the present cosmic time slice. There is a way to understand the division by the scale factor. Cosmologists sometimes introduce conformal time, a rescaled clock, so that light crosses equal co-moving distances during equal conformal time intervals. Cosmic time asks how much aging occurs for co-moving observers. Conformal time asks how much causal reach light accumulates on the co-moving map. The two clocks agree only when the scale factor remains fixed. When the early scale factor is small, an interval of cosmic time contains a larger interval of conformal time. This is why an old universe and a wide causal map cannot be compared through age alone. The horizon depends on the total conformal time available. No observer carries a conformal time wristwatch, and no second time replaces aging. It is a mathematical relabeling that exposes the geometry of signal propagation. In a diagram using conformal time and co-moving distance, light rays can be drawn at 45-degree angles, while expansion information is transferred into the relationship between conformal time and cosmic time. The diagram simplifies causal structure without changing any local measurement. This is the operation hidden behind the familiar 46.5 billion light-year radius. It is tempting to describe the calculation by saying that space stretched the photon's completed path after the photon passed. That image is incomplete. Expansion changes the relationship between proper and co-moving distance throughout the entire journey. Every interval is converted using the scale factor belonging to that interval. The final result is not an old path measured once and enlarged afterward. It is the accumulation of locally ordinary steps across an evolving geometry. A simplified universe shows how strongly the answer depends on expansion history. Consider an ideal universe containing only pressureless matter, with flat spatial geometry and no cosmological constant. Cosmologists call this the Einstein de Sitter model. In that universe, the scale factor grows in proportion to cosmic time raised to the power of 2/3. Substituting that history into the horizon integral gives a remarkably simple result. The present particle horizon radius equals 3 times c multiplied by the universe's age. If such a universe were 13.8 billion years old, its horizon radius would be roughly 41.4 billion light-years, not 13.8 billion. Even this stripped-down expanding model already defeats the static calculation by a factor of 3. No acceleration is needed to make the present horizon larger than c times the age. The difference arises because light crossed early co-moving intervals, when their proper scale was smaller. Our universe is not Einstein de Sitter. Radiation influenced the earliest expansion. Matter later dominated. A dark energy-like component became important comparatively recently. The measured density fractions and expansion rate produce a different function, A of t, so the integral must be evaluated using that fuller history. Radiation and matter do not contribute in identical ways. Radiation energy density falls especially rapidly as the universe expands because the number density of photons decreases while each photon's wavelength is stretched. Matter density falls with increasing volume, but does not suffer that additional redshift loss. A cosmological constant, by definition, maintains constant energy density as the volume grows. The changing balance among these components changes the rate at which A evolves. Cosmologists often rewrite the horizon calculation using redshift or scale factor rather than cosmic time, because observations are naturally organized that way. The mathematical form changes, but the question remains the same. How much co-moving progress can light accumulate while the universe follows the expansion curve allowed by the evidence? Using parameters close to the standard Planck fit, produces a particle horizon radius, conventionally quoted, near 46.5 billion light-years. Different calculators and parameter choices may return values around 46.1 to 46.6 billion light-years. The diameter is twice the radius, giving the rounded figure of approximately 93 billion light-years. The number is therefore not a new fundamental constant. It is an output. Change the age, matter density, radiation content, spatial curvature, dark energy behavior, or expansion rate, and the function inside the calculation changes. A different viable cosmology would generally produce a somewhat different horizon. There is another boundary just inside the particle horizon that matters observationally. The cosmic microwave background was released at recombination, when the universe was about 380,000 years old, and the scale factor was roughly 1/1100th of today's value. The present co-moving distance to that last scattering surface is commonly quoted near 45.7 billion light-years, slightly less than the full particle horizon radius. The gap exists because the particle horizon asks how far any causal signal could have traveled since the early model boundary, whereas the microwave background marks how far ordinary photons have freely traveled since the plasma became transparent. Before recombination, photons existed, but they scattered continually and could not carry an undisturbed image across the cosmos. Other messengers, such as relic neutrinos or primordial gravitational waves, could in principle reveal earlier epochs if they become observable with sufficient confidence. The particle horizon must also be distinguished from the Hubble sphere. The Hubble sphere is the distance at which the recession rate assigned by the Hubble law equals c at a particular time. Its position changes as the Hubble parameter changes. It is not generally the maximum distance from which signals can ever reach us. Photons emitted outside it can sometimes enter it later and arrive, depending on the expansion history. An event horizon answers yet another question. From which events emitted now could signals ever reach us, even given unlimited future time? Its existence and distance depend on how expansion behaves in the future. The particle horizon concerns what could have influenced us by now. The event horizon concerns what can influence us eventually. Mixing these boundaries creates apparent contradictions that belong to definitions, not nature. We can now audit the photon's receipts mathematically. The travel time receipt adds all the dt intervals and obtains nearly 13.8 billion years. The local motion receipt examines every interval separately and finds c. The present distance receipt converts each interval by dividing by its scale factor, adds the resulting co-moving steps, and obtains a radius near 46.5 billion light-years in the standard model. Nothing is counted twice. Nothing crosses its local surroundings faster than light. The large number appears because the receipts perform different sums. Yet one crucial question remains. The integral will produce any radius we ask for if we insert an arbitrary expansion curve. The calculation becomes science only when observations determine which curves survive. Cosmologists must infer the age, density fractions, geometry, and scale factor history from patterns in real data, then check whether independent cosmic rulers agree. The arithmetic explains how 46.5 billion light-years is possible. The next stage must explain why that particular history is credible. The horizon integral is only as trustworthy as the expansion history placed inside it. To determine that history, cosmologists do not search for a ruler long enough to reach the edge of observation. They allow the universe to provide several rulers, clocks, and patterns of its own. The most powerful early reference is the cosmic microwave background. Its nearly uniform glow contains tiny temperature variations, often only a few parts in 100,000. When those variations are decomposed by angular scale, they form a sequence of peaks and valleys called the CMB power spectrum. Those peaks are not random decoration. Before recombination, ordinary matter, electrons and photons formed a coupled plasma. Gravity pulled overdense regions inward, while radiation pressure resisted compression. The competition created acoustic oscillations, waves of compression and rarefaction moving through the young universe. Recombination released the photons and preserved a snapshot of those oscillations at different phases. The underlying physics supplies a characteristic scale. How large that scale appears on the sky depends on its actual size, and on the geometry and expansion history between the last scattering surface and us. It is similar in function to recognizing an object of known dimensions in a distant image. Although the cosmic ruler is calculated from plasma physics, rather than manufactured. The relative heights and positions of the peaks encode additional information. They respond to the densities of ordinary matter and dark matter, the amount of radiation, the initial fluctuation pattern, spatial geometry, and other parameters. Polarization provides further structure, while gravitational lensing of the microwave background traces intervening matter. A successful model must explain many features simultaneously, not merely one chosen peak. Kobe first measured the microwave spectrum with extraordinary precision and detected primordial anisotropy on large angular scales. WMAP then produced detailed full-sky maps and sharply improved estimates of the universe's age and composition. Planck measured smaller angular scales, polarization and lensing with still greater sensitivity. Within the 6-parameter, spatially flat lambda CDM model, Planck's final analysis inferred an age of approximately 13.797 billion years, with a quoted model-conditioned uncertainty of about 23 million years. It inferred a present Hubble parameter near 67.4 kilometers per second per megaparsec, and a matter density fraction near 0.315. The remaining dominant fraction is associated with a cosmological constant in the baseline model, with smaller contributions from radiation and other components. These impressive error bars require careful interpretation. Planck did not operate a clock for 13.797 billion years, nor did it measure the Hubble parameter by directly timing one galaxy's recession. The collaboration fitted a cosmological model to the statistical patterns in the CMB, including calibration and instrumental uncertainties. The age and expansion parameters are inferred values conditional on that model. Their precision shows how tightly the data constrain lambda CDM, not that every possible cosmology is known with the same certainty. The microwave background anchors the early universe, but a reliable expansion history must also pass tests at later epochs. Type Ia supernovae provide one such test. After their light curves are standardized, their apparent brightness supplies relative distances. Their host galaxy redshifts indicate the accumulated expansion. Plotting distance against redshift reveals that late expansion accelerated, ruling out the simplest matter-only histories. Supernovae are powerful at comparing distances across redshift, although their absolute calibration, dust corrections, population changes, and selection effects require continuing scrutiny. Baryon acoustic oscillations provide another ruler. The same pressure waves that left patterns in the microwave background also influenced the distribution of ordinary matter. After photons decoupled, a preferred separation scale remained imprinted statistically in the clustering of galaxies and intergalactic gas. Surveys do not find galaxies arranged on perfect shells. They detect a slight excess probability for pairs to occur at a characteristic separation. Because the physical origin of that scale is connected to early universe physics, its apparent size at different redshifts traces expansion. Across the sky, it constrains transverse distance. Along the line of sight, it constrains the expansion rate. Large galaxy surveys, including the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument, use millions of objects to measure this statistical feature across cosmic time. The probes are valuable precisely because they do not all make the same assumptions or suffer the same systematics. The CMB observes ancient radiation and infers a long integrated history. Supernovae compare standardized luminosities in the later universe. Bao uses a statistical clustering scale. Local distance ladders calibrate nearby stars and supernovae to estimate the current expansion rate. Weak gravitational lensing and structure growth test how matter clustered under the same cosmic model. Cosmologists combine these datasets by asking which parameter values allow one expansion history to satisfy them together. A model that fits the CMB but predicts the wrong supernova distances is incomplete. A model matching late expansion but destroying the acoustic peak pattern also fails. Agreement across probes narrows the allowed family of scale factor curves. Model fitting also accounts for correlations among parameters. A different matter density can imitate a change in expansion rate, while curvature can alter how a known scale appears on the sky. Combining observations breaks many of these degeneracies. The horizon value becomes persuasive not because one parameter is assumed perfectly, but because the same parameter set must survive several geometrical and physical tests at once. Once a curve is selected, the particle horizon is derived. Researchers calculate the age by integrating the inverse expansion rate through history. They calculate co-moving distance by integrating light propagation through that same history. The age and horizon are therefore related outputs of a shared model, not two unrelated measurements, accidentally found to disagree. This process also locates the last scattering surface. The CMB was emitted around redshift 1090, when the scale factor was roughly 1 part in 1091 of today's value. Its photons have traveled for nearly the age of the universe. Under standard parameters, the emitting region is assigned a present co-moving distance, commonly quoted around 45.7 billion light-years. The full particle horizon lies slightly farther, near 46.5 billion light-years, because causal history extends earlier than the release of freely streaming light. No telescope sees a label reading 45.7 billion light-years. The telescope measures frequencies, intensities, angular patterns, polarization, and correlations. The distance emerges after those observations are interpreted through a cosmological geometry. This does not make the result arbitrary. It makes its chain of inference explicit and testable. The strength of the chain appears in prediction. A model fitted to some features must correctly describe others. The hot Big Bang predicted relic radiation before its discovery. The physics of acoustic oscillations predicted a structured peak pattern that increasingly precise missions measured. A cosmology calibrated by the CMB predicted a statistical standard ruler in later matter clustering. Supernovae independently exposed acceleration, and BAO helped trace the same late expansion. The agreement is not perfect. Measurements of today's Hubble parameter, made through the local distance ladder, tend to produce values higher than the Planck lambda CDM inference. This Hubble tension may reflect unidentified systematic effects, new physics, or some combination. Recent DESI analyses have also strengthened interest in models where dark energy evolves, although the evidence depends on which datasets are combined and has not established a replacement for a cosmological constant. These tensions matter because the horizon is a derived quantity. If the true expansion history differs, its precise numerical value changes. But the existence of open questions does not return cosmology to the static model. CMB redshift, galaxy expansion, supernova acceleration, and BAO structure all require a dynamic history. The uncertainty concerns its exact form and parameters. The standard value near 46.5 billion light-years should therefore be spoken with two kinds of confidence. The qualitative result is extremely robust. Present co-moving distance to the observable limit greatly exceeds c multiplied by the cosmic age. The precise rounded radius is conditional. It reflects the expansion history favored by the current baseline model and data. The evidence has now supplied what the integral demanded. The scale factor was smaller in the past. Its rate changed as radiation, matter, and dark energy altered the cosmic balance. Multiple observations constrain that sequence, and integrating light's co-moving progress through it yields the horizon. Yet the result still appears to collide with relativity. If the emitting region is now more than 3 times as many light-years away as the photon traveled in years, its separation from us must have grown extraordinarily quickly. At sufficiently great distances, the recession rate assigned by the cosmological model can exceed the speed of light. That statement sounds like the forbidden answer from the beginning. To see why it is not, we must distinguish a speed measured locally from a rate of separation defined across an evolving spacetime. The difference will change what the original paradox was asking. The phrase "faster than light" can describe two very different calculations. One is forbidden by relativity. The other appears naturally in an expanding universe. Special relativity states that no material object can pass a nearby observer at or above the speed of light, and no local signal can carry information faster than light. The word "nearby" matters. Speed is directly measured when object and observer meet within the same local region, compare rulers and clocks, and determine how quickly one passes the other. Our photon obeys that rule everywhere. Every local observer along its path measures c. No measurement station records a violation. No galaxy locally sees the photon crawling, stopping, or accelerating beyond light speed. Cosmological recession rate is constructed differently. Take 2 distant markers carried with the average expansion. Choose a cosmic time slice, and calculate their proper distance along that slice. Wait a small interval of cosmic time, construct another slice, and calculate again. The rate at which that proper distance changes is their recession rate in the chosen cosmological coordinates. For the ideal large-scale expansion, recession rate equals the Hubble parameter multiplied by proper distance. Nearby markers have modest recession rates. More distant markers have larger ones, because more expanding interval lies between them. Beyond a sufficient distance, the product exceeds c. This does not describe either marker blasting past a local observer faster than light. They occupy different locations, and comparing their velocities requires a convention for relating separated frames across curved, evolving spacetime. The Flurga recession rate is useful and physically meaningful within its cosmological coordinates, but it is not the same quantity as a local special relativistic velocity. The distinction can feel like wordplay until we return to the photon. A comparison cannot reproduce this distinction. 2 rockets passing one observer possess comparable velocities, so velocity addition prevents either from being measured above c. Galaxies separated by billions of light-years do not share a laboratory. Their recession rate is obtained by comparing distances across the cosmological model, which is why the rocket rule cannot be transferred. Imagine a photon emitted toward us by a galaxy whose proper distance is increasing at more than say in the cosmological description. Locally, the photon moves toward us at c. Yet across the enormous separation, expansion initially adds proper distance faster than the photon removes it. The photon approaches us in co-moving coordinates, while its proper distance from us grows. Nothing has reversed its local direction. Nothing has pushed it backward. The proper distance curve rises, because that distance contains the changing scale factor, as well as the photon's coordinate position. As cosmic history continues, the Hubble parameter changes. The boundary at which recession rate equals c can shift. The photon may eventually enter a region where expansion adds less proper distance than the photon removes. Its proper distance reaches a maximum, begins to fall, and finally reaches zero when the photon arrives. The boundary where recession rate equals c is called the Hubble sphere. It is sometimes mislabeled as the edge of the observable universe, but the two are not identical. The particle horizon marks the most distant co-moving origin from which a signal could have reached us by now. The Hubble sphere marks where recession rate equals c at one particular cosmic time. Because its location evolves, it need not act as a one-way barrier. This is not only a mathematical possibility. In standard cosmology, we observe light from galaxies whose cosmological recession rates were, and in many cases remain, greater than c. Their photons reached us without violating local relativity, because the expansion history changed the relationship between their trajectory and proper distance. The result also corrects the image of galaxies crossing a fixed boundary at light speed. A distant galaxy's recession rate can exceed c without emitting any locally superluminal signal. We cannot use that recession to send information faster than light between neighboring laboratories. Causal influence still follows light cones. General relativity changes the global geometry in which those cones are connected. It does not abolish them. At this point, the original paradox changes category. We began by imagining the observable universe as a container, whose radius must equal the maximum distance a photon could physically traverse through static space. If that radius exceeded c multiplied by age, something seemed to have outrun light. But the 46.5 billion light-year radius is not the length of one fixed corridor crossed by a photon. It is the present proper value of a co-moving separation reconstructed on today's cosmic time slice. The photon's path connects an ancient emission event to our present observation event. The horizon radius asks where the corresponding origin lies on a different geometrical construction. The map of co-moving locations evaluated now. The path and the present separation are related, but they are not identical measurements. This is the midpoint reversal. What looked like a problem about forbidden speed is really a problem about comparing distances across time. The invariant local statement remains simple. Light moves at c. The larger cosmological statement requires a scale factor, a chosen time slicing, and an expansion history. When these are supplied, recession above c and observation of superluminally receding regions can coexist. The change in viewpoint also explains why replacing the words galaxy motion with space expanding is not enough. Saying space can expand faster than light can easily suggest that space is a substance with a measurable local speed. The more careful statement is that the proper separation between sufficiently distant co-moving locations can increase at a rate greater than c in Flavu coordinates. No object locally passes another at that rate. Different coordinates can assign different global recession descriptions, which is another reason not to treat recession rate as an ordinary local velocity. The observable predictions remain coordinate independent. The redshifts, arrival of photons, relationships among measured distances, and causal accessibility of events. Coordinates organize those facts. They do not manufacture them. The event horizon provides a final contrast. It marks the boundary separating events whose signals can ever reach us from those that cannot, assuming a specified future expansion history. A photon emitted beyond the present Hubble sphere might reach us if conditions evolve favorably. A photon emitted beyond a true event horizon never will. In a universe with sustained accelerated expansion, such an event horizon can exist, but its exact behavior depends on what dark energy does in the future. We therefore have three boundaries answering three questions. The Hubble sphere asks where recession equals C now. The particle horizon asks how far past influence could have reached us by now. The event horizon asks which present or future events can ever influence us. Treating anyone as a physical wall produces confusion. Our three receipts now align more closely. The local motion receipt never exceeds c. The travel time receipt remains almost 13.8 billion years. The present distance receipt can still say 46.5 billion light-years because it concerns a global separation assembled from an evolving geometry, not a locally measured velocity multiplied by time. The speed limit objection is therefore resolved. Nothing had to outrun light through its immediate surroundings. The apparent violation came from applying a local rule to a global quantity with a different definition. But solving the conceptual paradox does not make the numerical answer exact. The 46.5 billion light-year radius follows from one best-fitting expansion history. Change that history, and the integral changes. The next question is no longer whether the result violates relativity. It is how firmly observations determine the cosmic recipe that produces the number 46.5. The number 46.5 billion light-years is often repeated as though cosmologists discovered a perfectly marked boundary. In reality, it is the rounded answer produced by a particular cosmic recipe. That recipe is lambda CDM. Lambda represents a cosmological constant, the simplest mathematical description of dark energy. CDM stands for cold, dark matter, whose particles move slowly compared with light when structure begins forming. Add ordinary matter, radiation, neutrinos, an early pattern of fluctuations, and an approximately homogeneous geometry, and the model can describe an enormous range of observations with only a small set of central parameters. Within this framework, Planck's microwave background data constrain the parameters tightly. The resulting age and particle horizon appear precise. But precision inside a model is not identical to certainty that the model contains every ingredient. Imagine measuring the dimensions of a room from several echoes, while assuming the walls are flat. If the echoes fit that geometry extremely well, the inferred dimensions may have tiny statistical uncertainty. Yet if one wall has an unexpected curve, the quoted error bars do not automatically include that missing possibility. They describe uncertainty given the model, not uncertainty over every conceivable model. Planck's age of 13.797 billion years with a 23 million year uncertainty should be understood this way. It is an exceptionally precise inference under base lambda CDM. Allow additional curvature, evolving dark energy, extra relativistic species, unusual neutrino behavior, or changes to early expansion, and the permitted parameter ranges can shift. Age estimates from stars provide a sanity check. Stellar evolution carries uncertainties, but the oldest stars must not be older than the universe containing them. Modern stellar ages fit beneath the cosmological age. This agreement does not calculate the particle horizon, yet it helps prevent a fitted CMB model from drifting into a timeline incompatible with astrophysical history. The most famous sign that the baseline picture may be incomplete is the Hubble tension. Planck infers today's Hubble parameter by fitting the early universe CMB and evolving the lambda CDM model forward. The result lies near 67.4 kilometers per second per megaparsec. Local distance ladder programs build upward from geometric calibrations to Cepheid variables or other stellar indicators, and then to Type 1a supernovae. Prominent analyses obtain values near 73 kilometers per second per megaparsec. The difference is too large to dismiss casually, but its meaning remains unsettled. Some systematic error may remain in one or more measurements. New physics before recombination might change the calibration that converts the CMB pattern into late-time parameters. The dark energy sector, or gravity, might differ from the baseline model. Researchers continue testing every link. For the horizon calculation, it would be incorrect simply to replace 67.4 with 73, while leaving all other Planck parameters unchanged. Cosmological parameters are correlated. A model that changes the expansion rate may also change the inferred age, sound horizon, matter density, or early history. A scientifically consistent alternative must be fitted to the full set of observations, and then integrated. The Hubble tension, therefore, does not translate into one automatic percentage correction to 46.5 billion light-years. It warns that the precise expansion curve may require revision. Dark energy creates a second precision gap. In lambda CDM, its density is constant, and its pressure has a particular negative relationship to that density. This simple assumption reproduces much of the evidence. But the physical origin of the cosmological constant remains unexplained, and the observed vacuum energy scale poses a profound theoretical problem. The dark energy spectroscopic instrument has mapped the positions and redshifts of millions of galaxies and quasars, measuring baryon acoustic oscillations across a vast span of cosmic history. Recent DESI analyses, when combined with selected CMB, supernova, and other datasets, have strengthened hints that dark energy might evolve rather than remain constant. Hints are not discoveries. Their statistical strength depends on which supernova compilation and dataset combination is used. Systematic effects and model choices remain under investigation. Lambda CDM continues to serve as the baseline, while evolving dark energy models are being tested against larger and more diverse data. If dark energy evolves, the late portion of the scale factor curve changes. The present particle horizon would shift somewhat, because every interval contributes to the integral. Predictions for the future event horizon could change more dramatically, since they depend entirely on expansion that has not yet occurred. This is why assigning one exact permanent future boundary is less secure than describing the present particle horizon under an identified model. Spatial curvature offers another possible adjustment. A universe can be spatially flat, positively curved, or negatively curved on large scales. Planck data combined with other probes strongly favor geometry close to flat. But close to flat does not prove that the global universe is exactly Euclidean, or determine whether its spatial extent is finite. Small curvature changes relationships among angles, distances, and volumes, and can alter inferred cosmological parameters. Topology is different from curvature. A flat universe could be infinite, or it could possess a finite multiply-connected topology, much as a video game space might reconnect across boundaries. Searches for repeated patterns in the microwave sky constrain some possibilities, but they have not measured the total size. The 93 billion light-year observable diameter remains compatible with a much larger total universe under many global geometries. The earliest cosmic history also matters. The horizon integral is commonly written from a formal time zero within the classical model, but known physics cannot reliably describe an initial singularity. Inflation, if it occurred, preceded the conventional radiation-dominated hot Big Bang and altered causal structure. Specific inflationary models differ, and no unique model has been established. For today's particle horizon number, the overwhelming contribution is treated through the standard post-inflationary expansion history. Uncertainty about the earliest fractions of a second does not usually turn 46.5 into 13.8. But it prevents the lower limit of the integral from being described as a directly understood physical beginning. Neutrinos and radiation add smaller dependencies. The amount of relativistic energy changes early expansion. Neutrino masses affect both background evolution and structure formation. Parameter fits include assumptions about these components, and future measurements may refine them. Again, the lesson is not that any value is possible. It is that the final decimal places belong to a network of assumptions and constraints. We can separate the conclusion into 3 levels of confidence. First, the static calculation is wrong for the real universe. Redshift, the microwave background, supernovae, and large-scale structure establish an evolving cosmology. Present co-moving distance to ancient sources cannot be obtained by multiplying lookback time by c. Second, a particle horizon radius of roughly 46 billion light-years is robust across models, close to the observationally successful standard history. The commonly quoted 46.5 billion light-year radius and 93 billion light-year diameter are responsible rounded summaries. Third, the exact value is conditional. It is not appropriate to imply that 46.50 billion light-years has been directly measured or will remain unchanged after every future dataset. Model extensions and improved parameters can move it. This hierarchy protects the answer from 2 opposite mistakes. One is false certainty, presenting lambda CDM as complete and the horizon as an observed wall. The other is false skepticism, treating open tensions as though cosmologists know nothing about expansion or distance. The evidence permits a strong explanation without granting final precision. The photon remains unaffected by this debate in one crucial respect. Whichever viable expansion history ultimately wins, its local speed is c. The calculation must still distinguish travel time from present co-moving separation. A revised model may change the third receipt's number, but it will not make all 3 receipts collapse into the static formula. The paradox has therefore survived every uncertainty test. Its resolution does not depend on one disputed decimal place or one specific dark energy theory. What remains is to show why the broad cosmic recipe is more than a collection of adjustable ingredients. The observations that measured age, composition, geometry, clustering, and acceleration are interconnected consequences of one expansion history. When those clues are placed on the same timeline, discoveries that appeared separate begin to converge. The universe's oldest light, the spacing of galaxies, the brightness of dying stars, and the growth of structure all become different readings of the same evolving rulebook. The evidence becomes most powerful when it is arranged not by telescope or discovery date, but along one curve, the scale factor through cosmic time. Near the beginning of the hot Big Bang description, the universe was filled with radiation and rapidly moving particles. Radiation density fell steeply as expansion increased the available volume and stretched every photon's wavelength. During this era, the scale factor followed one characteristic growth pattern, and the co-moving reach accumulated by light depended on that pattern. As radiation diluted, matter became dominant. Matter density also fell as volume increased, but rest mass did not lose energy through wavelength stretching in the same way. Gravity gathered small density differences into larger structures. Dark matter began building gravitational frameworks. Ordinary gas later fell inward, cooled, and formed stars and galaxies. Expansion continued, but its rate evolved differently from the radiation era. At comparatively late times, the component called dark energy became important to the dynamics. In the baseline model, its density remains constant while matter thins. Expansion shifted from deceleration to acceleration. The scale factor curve changed character again. These are not three disconnected stories. They are three regimes of one equation, whose terms gain or lose relative importance. The cosmic microwave background anchors the transition from the opaque plasma to the transparent universe. Its thermal spectrum records a hot origin. Its temperature and polarization fluctuations record acoustic motion, matter content, geometry, and initial density variations. The observed angular size of the acoustic pattern depends on the distance that light traveled from recombination through every later era. The CMB therefore looks backward and forward at once. Its microphysics belongs to the early universe, but the angle under which we observe that pattern depends on the expansion between then and now. Alter the late expansion history, and the inferred distance to last scattering changes. Alter the matter density and both the early oscillations and later geometry respond. Baryon acoustic oscillations carry a related scale into the distribution of matter. The early plasma wave establishes the standard ruler. Galaxy and gas surveys recover its statistical imprint at later redshifts. Measuring that ruler at several epochs samples the expansion curve between the CMB and the present. Type Ia supernovae add another reading. Their standardized brightnesses provide relative luminosity distances, especially across the era in which acceleration becomes visible. They do not reproduce the BAO method, and that independence matters. When supernovae and BAO favor compatible late histories, two different physical systems point toward the same changing geometry. The growth of structure supplies a further test. Expansion and gravity compete. Matter clumps more efficiently under some histories than others. Galaxy clustering, weak gravitational lensing, and the evolution of large structures therefore test whether the matter content and expansion curve inferred from background geometry also produce the observed cosmic web. Even primordial element abundances join the timeline. Big Bang nucleosynthesis depends on the early expansion rate, baryon density, and thermal history during the first minutes. It does not calculate today's horizon directly, but it constrains a cosmic recipe that must remain compatible with the much later CMB and galaxy observations. The success of lambda CDM lies in this convergence. A small parameter set describes the primordial acoustic pattern, the abundance of matter, the geometry to last scattering, later clustering scales, supernova distances, and structure growth with remarkable overall consistency. The model is not flawless, but its parameters cannot be adjusted independently for every dataset without consequences elsewhere. This is why the particle horizon is not an arbitrary number chosen after observations. The same scale factor history used to calculate it must also carry the sound horizon from the early plasma to the BAO pattern. Place the CMB peaks at their observed angles, produce a plausible age for old stars, fit late supernova distances, and permit the observed formation of structure. One word now creates an important danger: horizon. The particle horizon in our title is the maximum co-moving distance from which a causal signal could have reached us by the present. The classic horizon problem is a different question about the early universe. It asks why widely separated regions of the CMB possess nearly the same temperature, even though, in a simple hot Big Bang model, without an earlier accelerated phase, they appear not to have been in causal contact before recombination. Imagine two opposite patches on the last scattering surface. Today their light reaches us from different directions. Reconstruct their past, using only the standard radiation and matter-dominated expansion, and their causal regions before recombination do not overlap enough to explain the observed uniformity through ordinary equilibration. Yet their temperatures agree to extraordinary precision, apart from the tiny fluctuations that seeded structure. Inflation is the leading solution. It proposes that before the conventional hot radiation era, the universe underwent a brief period of accelerated expansion. Regions that began close enough to exchange influences were stretched to separations far beyond the pre-inflationary causal scale. After inflation ended and the universe reheated, those once connected regions could appear widely separated across the microwave sky. Inflation also helps explain why spatial geometry appears so close to flat and provides a mechanism for generating primordial fluctuations from quantum processes. The measured pattern of nearly scale-invariant, predominantly adiabatic fluctuations is broadly compatible with inflationary expectations. But inflation is a framework containing many models, not one uniquely verified event with a known field and potential. No definitive primordial gravitational wave signature has selected a specific mechanism. Alternatives and extensions remain under investigation. The responsible statement is that inflation is the leading explanation for the early horizon and flatness problems, with important predictions supported, but its fundamental physics unsettled. Inflation must not be used as a shortcut answer to why today's particle horizon radius is 46.5 billion light-years. That radius is conventionally obtained by integrating the expansion history across the hot Big Bang era to the present, with early boundary assumptions. Inflation sets earlier causal conditions and can make the full universe far larger than our observable patch. It does not replace the scale factor arithmetic already performed. This distinction reveals a deeper progression. At first, the observable universe seemed like a physical object whose size should be age multiplied by light speed. Then, it became a set of co-moving relationships defined by causal signals. Now even that observable region appears as one patch within a potentially much larger spatial whole, shaped by physics that precedes the oldest light we can see. Observational flatness does not prove infinity. A surface can look flat across a small surveyed region while curving on a vastly greater scale. Inflation often predicts a universe much larger than the observable domain, but the total extent depends on the model. Space might be infinite, finite and unbounded, or connected through a topology too large for repeated patterns to appear within our horizon. The 93 billion light-year diameter therefore belongs to causal history, not to a census of all existence. It tells us how far influence could have propagated to one observer under the reconstructed expansion. It does not tell us how much unobserved space continues beyond that limit. Return now to the single ancient photon. Its microwave wavelength reflects the change in scale factor since recombination. The angular pattern surrounding it reflects pressure waves in the early plasma. The galaxies it later passed belong to structures grown from the same primordial variations. Their clustering retains the acoustic scale. Exploding stars within later galaxies reveal acceleration. Every stage of the photon's journey crosses evidence that calibrates the geometry used to place its origin on today's map. The photon is not merely a messenger traveling through the model. It is part of the evidence from which the model is constructed. Separate observations now converge into one explanatory system. General relativity permits dynamic geometry. The Hubble-Lemaître relation reveals expansion. The CMB records early conditions. Nucleosynthesis tests the initial thermal history. BAO transports an early ruler into later structure. Supernovae reveal acceleration. Structure growth tests the gravitational consequences. Together, these determine the broad scale factor history, whose conformal time sets the observable radius. Live tensions do not erase this convergence. They ask whether the baseline curve needs a controlled modification. Any replacement must explain at least as much evidence, not only one discrepancy. It must preserve the successful links among early physics, late distances, and structure, while improving the points of tension. Only a model that keeps these connections intact can replace the standard horizon estimate with another value. All the necessary threads have now reached the same place. We know what the 3 photon receipts measure. We know why local light speed remains c. We know why early intervals contribute more present co-moving distance. We know how observations constrain the expansion curve, and we know where its precision may change. The final task is no longer discovery. It is reconciliation. We can now read the receipts together, perform the title's arithmetic with the correct geometry, and state exactly why 13.8 billion years becomes a radius near 46.5 billion light-years, without turning either number into something it is not. We can finally place the 3 receipts beside one another and ask what each has actually measured. The first receipt is the age of the universe. Under the standard lambda CDM model fitted to Planck data, cosmic time since the early hot Big Bang is approximately 13.8 billion years. That is the time available for causal processes within the modeled history. It is measured in years because it answers a question about elapsed time. The second receipt belongs to the photon. At every local stage of its journey, it moves at c. If we divide its path into arbitrarily small laboratories, each observer measures the same light speed. Expansion does not add a hidden boost to that local motion, and no interval records the photon breaking relativity. The third receipt is the present co-moving distance to the photon's region of origin. It asks where that co-moving location belongs on today's cosmic map, after accounting for how the scale factor changed throughout the journey. Under the standard fitted expansion history, the particle horizon radius is approximately 46.5 billion light-years. These values look inconsistent only if the third receipt is calculated as though it were the second. In static space, we would add all the small time intervals and multiply the result by c. 13.8 billion years would then correspond to 13.8 billion light-years. But cosmological co-moving distance performs a different sum. For every interval, it takes the local distance c times dt and divides by the scale factor that existed during that interval. It then adds those converted steps. Early in history, the scale factor was far below 1. A local step crossed more units of the compact co-moving grid than the same proper step crosses today. When that early coordinate interval is evaluated on today's ruler, it represents a much larger proper distance. Later intervals, occurring when the scale factor was closer to 1, receive less conversion. The complete operation is the particle horizon integral, c multiplied by the accumulated dt divided by a of t. Insert the expansion history constrained by the microwave background, matter density, baryon acoustic oscillations, supernova distances, and other evidence. The result is not c times 13.8 billion years. It is a present co-moving radius, near 46.5 billion light-years. Now draw a sphere around the observer. The horizon radius extends approximately 46.5 billion light-years in every direction on today's co-moving map. A line across the entire sphere passes through the observer and continues to the opposite horizon. Twice 46.5 gives approximately 93 billion light-years. That is the origin of the title's diameter. No photon crossed the full diameter. Light arriving from one side traveled to us. Light arriving from the opposite side also traveled to us. The two horizon regions cannot send us information about their present conditions, and we are not seeing both endpoints as they exist on today's time slice. The 93 billion light-year figure is a reconstructed present separation across our observable region, not the length of a beam's completed journey. The cosmic microwave background gives the most visible version of this geometry. Its photons began freely streaming about 380,000 years after the hot Big Bang. They have traveled for nearly 13.8 billion years. The regions that emitted them are assigned a present co-moving distance near 45.7 billion light-years, slightly inside the particle horizon. The extra interval to roughly 46.5 billion represents causal reach earlier than the transparent surface, not a farther electromagnetic photograph. We can now read the receipts as a complete sentence. For approximately 13.8 billion years, light moved locally at c through a universe whose scale factor changed. Converting each local step to today's co-moving ruler and adding the steps places the particle horizon near 46.5 billion light-years in every direction. Doubling that radius gives an observable diameter near 93 billion light-years. The ratio between radius and age is not a universal law. It summarizes this universe's measured history. In another expanding universe, the same light speed and the same age could accompany another horizon radius. The number today carries a record of what dominated expansion, and when each component became important. Nothing traveled locally across 93 billion light-years in 13.8 billion years. Nothing needed to. This answer also explains why acceleration alone is not the solution. Even a flat matter-only expanding universe has a particle horizon larger than c, multiplied by its age. The essential effect is that the scale factor was smaller in the past. Radiation, matter, and dark energy determine the detailed curve and therefore the precise multiplier, but dynamic geometry creates the basic difference. Nor does the answer depend on imagining space as a substance moving faster than light. The relevant global quantity is the changing proper separation between distant co-moving world lines. Such a recession rate can exceed sane in Flage coordinates, because it is not a local velocity measured as one object passes another. Every local causal signal remains constrained. The three receipts therefore do more than resolve one numerical puzzle. Together, they reveal three layers of cosmological knowledge. The age is inferred from a model that must reproduce ancient radiation and later observations. The local speed is governed by relativity and measured in small neighborhoods. The horizon is a global, model-derived distance, defined on a particular cosmic time slice. Confusion appears when a rule belonging to one layer is forced onto another. The strongest answer can now be stated without metaphor. The observable universe is approximately 93 billion light-years across today, because the present co-moving distance reached by causal signals is calculated through an expanding LRO spacetime, not through static Euclidean space. The finite age limits how long signals have propagated. It does not require their source's present separations to equal c multiplied by that age. But the word approximately carries scientific responsibility. No detector has touched the particle horizon. The radius is derived from the scale factor history. Planck's small uncertainties describe lambda CDM parameter inference, and viable extensions can shift the result. The Hubble tension remains unresolved. DESI and other surveys are testing whether dark energy evolves. Early universe physics and spatial topology remain incomplete. Future evidence may refine. 46.5. A different best-fitting expansion history might move the conventional horizon by some amount. It could revise the age and distance together. Yet any successful replacement must still explain the microwave peaks, BAO ruler, supernova distances, structure growth, and local measurements. It cannot merely choose a preferred radius. This limitation does not undo the achievement. Whether a refined value is 46.5 or modestly different, the observable radius will not collapse to 13.8 billion light-years unless the entire evidence-supported expansion history is abandoned. The qualitative resolution is far more secure than the final digits. There is a larger exception. The particle horizon calculation gives the extent of our observable region, not the extent of the entire universe. Beyond the horizon may lie continuing galaxies and space, whose signals have not reached us. Inflationary models often imply a domain vastly larger than our observable patch, and spatial flatness is consistent with infinity, but neither establishes the total size. The title can therefore mislead in two opposite directions. It appears to make the observable universe too large for its age, while it may describe a sphere far smaller than the universe as a whole. The first confusion is resolved by expanding geometry. The second remains an open frontier because observation is bounded by causal contact. Return once more to the arriving photon. Its wavelength tells us how much the universe expanded since emission. Its surrounding microwave pattern helps determine the cosmic recipe. Its travel obeys the local speed limit. Its source is placed on today's map through the horizon integral. One signal participates in every layer of the answer. The photon did not bring us a picture of a wall. It brought evidence from which we reconstructed a geometry. 13.8 billion years and 46.5 billion light-years are therefore not rival claims. One tells us how long cosmic history has unfolded. The other tells us how that history maps causal reach into present distance. 93 billion light-years is the diameter obtained when that reach is extended in opposite directions around us. The numerical paradox is finished. What remains is the meaning of the boundary. If the horizon is not an edge of space, what exactly ends there? Not the universe, but our present map of causal evidence. The final step is to distinguish the limit of observation from the limit of reality. The answer can now be stated plainly. The universe can be about 13.8 billion years old, while our observable region is approximately 93 billion light-years across, because age and present distance measure different things. Light has propagated locally at sea through an expanding spacetime. When every step of that journey is translated onto today's co-moving ruler, the maximum causal reach is about 46.5 billion light-years in each direction under the standard cosmological model. The diameter is twice that radius. It is not the distance one photon traveled, and it is not evidence that matter crossed its local surroundings faster than light. But the phrase observable universe is now more important than the number. The particle horizon marks the boundary of events that could have influenced us by the present. It is centered on our location, because this is our causal map. An observer in a galaxy billions of light-years away would construct a different sphere centered there. Neither observer occupies the center of all space. Each occupies the center of the region from which information has reached that observer. At the horizon, nothing has to end physically. There is no known shell, wall, or sudden emptiness. The large-scale conditions we observe make it reasonable to expect that space and matter continue beyond our present view, but signals from sufficiently distant regions have not had a causal path to us. The boundary belongs to information. This is why the 93 billion light-year diameter cannot answer how large the entire universe is. Observations show that space is very close to geometrically flat across the accessible region. That finding permits an infinite universe, but does not prove infinity. A finite universe can also appear nearly flat if its curvature scale greatly exceeds our horizon. Its topology could connect space in ways whose repeated patterns lie beyond observation. Inflationary models often make the full domain vastly larger than our visible patch. Yet inflation does not provide one measured total size. The responsible answer remains that the universe extends at least as far as the observable region and probably much farther, while its complete extent is unknown. The future introduces another limit. The particle horizon asks which past signals could reach us by now. The event horizon asks which events can ever send signals to us, even with unlimited future time. If accelerated expansion continues indefinitely, some regions we can observe in their ancient state may never exchange newly emitted signals with us. Their old light arrives, while their future history becomes permanently inaccessible. Because the nature of dark energy remains under investigation, the exact future boundary carries additional model dependence. Current surveys can refine the expansion history and test whether acceleration follows a cosmological constant or an evolving component. They may change detailed horizon estimates. They will not turn the observable boundary into a material edge. Return to the photon that opened our investigation. It arrived carrying no clock and no written distance. We inferred its travel time from cosmic history. We confirmed its local speed through relativity. We used its wavelength, the microwave sky, galaxy clustering, supernovae, and the scale factor model to place its source on today's Comoving map. Its three receipts appeared contradictory only because we asked each to answer the other's question. The first receipt told us how long the journey lasted. The second told us how light moved through every local region. The third told us the present separation assigned to its origin after the universe changed scale. Once the labels were restored, 13.8 billion years and 46.5 billion light-years ceased to compete. The deeper lesson is not that ordinary intuition is foolish. The rule distance equals speed multiplied by time works brilliantly when geometry remains effectively fixed. Cosmology reveals the boundary of that rule's domain. Across the age and scale of the universe, distance is inseparable from the history of spacetime. Science has therefore answered the title without claiming more than the evidence allows. The expansion history explains why our observable diameter is near 93 billion light-years. Relativity explains why no local speed limit was broken. The particle horizon explains why this number describes causal access rather than total existence. Current tensions explain why the final digits remain open to refinement. What lies beyond the horizon is not necessarily stranger physics. It may simply be more universe, regions governed by similar laws, containing histories whose light has not reached us. We cannot include them in a direct census, and we cannot replace evidence with certainty. Their absence from our map is not evidence of their absence from reality. The oldest light does not show us the universe's outer wall. It shows us how far the past has been able to speak to us. 93 billion light-years is the width of that conversation today. Across the observable universe we can reconstruct now.